first speaker. I actually had some information in my opening presentation. Igal Raichelgauz from Israel. Please come up to me on the stage, Igal. You have one, okay. Okay. So, we're very grateful to have you here from Israel under these circumstances. You traveled here to give this speech. Really great thanks and great cheer from us.
Thank you.
You are a real, true expert in AI. The keynote you will be presenting now gets expectations very high. Liquid AI, closing the gap towards autonomous driving. I think that's exactly what we need.
Thank you.
Go ahead with your speech, and thank you very much for being here.
Thank you very much. So our company, Autobrains, develops Liquid AI. This is a new kind of AI compared to classical AI, traditional AI, that is based on supervised learning. And I will present you this AI and the gaps that is exposed to close to a more safe and more automated driving. So let's start with the existing state of the art. As you know, we already have millions of cars on the road with AI supporting ADAS systems, and this works very well. However, if we look at the gaps that are still there on the AI level, we will see three key gaps. The first one is related to the ability to address edge cases. And similar to every real-world AI problem, we are talking here about the long tail of edge cases. The second problem is related to cost, both cost of the system that goes into the car, as well as the cost that is associated with developing this AI in terms of training, data collection, and validation. The last gap is related to two key modules in the AI system. The perception module that is responsible for understanding the situation, the environment, and the second model that is responsible for the decision-making. Now, all AIs today are based on the same basic recipe, same basic approach. The AI community calls this AI narrow AI. Narrow due to the fact that it has a specific function. It focuses on a specific task that it's supposed to solve. Now, the recipe to improve this AI is more or less the same across all systems. It's about collecting data, labeling the data, training the system with this data, and then once the system exhausts itself in terms of computational resources, increasing the computational resources, having a deeper neural network, and then continue. So basically repeat until we are out of data or out of computational resources. The problem with this approach is that at a certain point, it doesn't scale well. At a certain point, we are getting into this area, which is called the diminishing returns of deep learning. And the reason is, again, this long tail of edge cases. So in order to improve the system 10 times in terms of its accuracy, 10,000 times are required in terms of computational resources, data, labeling, power consumption, and so on. Now, why? Why does this happen? Why we are getting into this diminishing return zone? So similar to every real-world AI problem, autonomous driving is about large, long tail of edge cases, co-occurrences of different situations related to occlusions, lighting conditions, unexpected situations. So on the problem side, we have this long tail of edge cases. But on the solution side, all the techniques today are based on optimizing the average case. Algorithms used in deep learning today, such as gradient descent and backpropagation, are all about minimizing the average error. So there is a disconnect. On one side, we are trying to optimize the system for the popular average cases, but on the other side, we have this challenge of a long-tail distribution. So what is the plan? How we scale those systems? If we look at the debates today within the AI community, one hope is that by using more data, more or deeper neural networks, more compute, the expectation that at some point, this narrow AI system will become a general AI. So there will be some emergence process, and the system will become better and better. However, there is also a much more fundamental question, and the question if such a general AI really exists. Can this narrow AI become a general AI, or whether this general AI exists at all? And the best way to ask ourselves what is general intelligence is to look at the best reference, the human intelligence. Now, if we look at the human intelligence, I think we'll all get convinced that there is no such thing as general intelligence. Human intelligence is composed of set of very specific narrow intelligences. Intelligence for math, intelligence for language, intelligence for spatial information, and so on. If we look even deeper into the brain, based on the work of one of the founders of deep learning, Marvin Minsky, or more recent work of Jeff Hawkins, we'll see that the brain is composed of a large ensemble of simpler, smaller brains. So there is really no one model, no one general model of everything that can solve a problem. And that's why I believe that the right approach today, instead of trying to invest more brute force resources at the same kind of AI, the narrow AI, and hoping to achieve a general AI by some miracle, to switch the paradigm and to focus on a different kind of AI that we call liquid AI. Now, I'll present two key principles of liquid AI. So the first one is that the architecture is not fixed. In all the classical approaches today of narrow deep learning, the architecture is handcrafted by a PhD or by a researcher. It reminds a bit the feature engineering before the deep learning that researchers did. So today, researchers are doing themselves manually the architectures. And this is a big challenge because the problem doesn't necessarily fit to predefined architecture. So here we are talking about architecture that is emerging during the learning process. And this architecture is supposed to map the problem with all its different edge cases. Now, we are not trying here to increase the parameters, to increase the complexity of the system. On the contrary, each such split, each bifurcation in this architecture is about identifying a more narrow problem and solving it either by a neural network, a branch of a neural network, or a representation generated by a neural network. The second principle directly goes into the solution to this long-tail problem. So instead of trying to increase one big narrow AI, we are going to the opposite direction. We are scaling the number of narrow AIs. So the idea is that each narrow AI models a separate part of this long-tail distribution, reusing the same approach that we know that is already working. This allows us a different dimension, another dimension, to scale the system and to improve it over time. So let's take this down to earth. Please look at this image. I'm sure all of you can see here a cat with an orange on its back, but I'm sure that also the AI practitioners here have in mind that any AI system might have a difficulty with such an image. It might confuse it with a fried sunny side up egg. And I saw this image for the first time after ChatGPT was launched and the image feature was released. I saw a post on LinkedIn basically saying, here is an image which was identified correctly by ChatGPT, and it's mind-blowing. We are always talking about the edge cases, and finally, we have a solution. And recognizing this image with the current state of AI is a strong signal that AI got to the level of human intelligence. And of course, there was a lot of posts after that showing the importance of this observation. If the existing AI can really recognize such a complicated, nuanced image, then we are in a completely different situation. So of course, I had to try it myself. And I injected this image into ChatGPT. And the result was quite amazing. ChatGPT really identifies this image, all the nuances. It understands that this is a cat with an orange on top of it. But it also says that this image could be confused with a fried egg. So ChatGPT even has this additional knowledge that we, mere human beings, might make such confusion, as we don't have trillions of parameters and so much training data. So I ask myself, if the state of the art today is at this stage, how come we cannot reuse the same AI for autonomous driving? Can't we just take ChatGPT or similar kind of AI, even if it's on cloud, even if it's very expensive and high compute, and connect one of the cars and show that we really can solve the autonomous driving problem? But of course, I also had my doubts about that. Around the same time, one of the leaders in the AI community, Jan LeCun, published that even with the most advanced large language models, such as ChatGPT, we are nowhere near the intelligence of a human being, even not a cat. And of course, ChatGPT is a great product, but it's great in reasoning, it's great in language, but it's not there in terms of understanding the real-world environment with all its nuances, with all its edge cases. So where is the disconnect? And here you can follow my expectations from ChatGPT results. So the first step I did is to take this specific image and insert it into Google image search just to test the water. And the results were very interesting. Google found a lot of images of exactly the same cat and exactly the same orange, basically showing near duplicates. So I had more doubts about it. Maybe this is a celebrity image, and what ChatGPT does is actually taking the text around all the debates around this specific image on social media, processing in a very nice manner, but doesn't really understand the content of this image. It pretends to understand, but it just processes the text around. So to nail this down, I had to find images of white cats with orange that are not from the web, not from the internet. Our 157 employees got a task to find white cats, convince them to curl up, to put an orange on their back, and take pictures. And that's what we did. So you can see here even a simpler image with this cat, and the output of ChatGPT was not as impressive as before. Yeah, you can see here basically that ChatGPT thinks now it's a fried egg. So where we are in terms of state of the art, I think we are back to the same problem. We have those huge models with the diminishing returns, but we also have on top of these models a large set of protective technologies, which are trying to make the AI job simpler, to reduce the AI job, to reduce the functionality. And ChatGPT is an amazing consumer product. But even with all these investments, I heard in one of the lectures, 170 trillion parameters, billions of dollars for development, millions or tens of millions of dollars for training infrastructure, we still cannot differentiate between cats and fried eggs. And the situation in the automotive industry, I believe, is quite similar. We have billions or tens of billions of dollars invested into the same kind of AI, same narrow AI, supervised deep learning-based AI. And in order to achieve a good product result, we are trying to protect this AI with a lot of different technologies, whether those are mapping or vehicle-to-vehicle communication or connecting to the cloud or more advanced sensors like LiDAR. And all of that, of course, increases the cost. It solves some parts of the problem, but it doesn't solve the key problem that is related to AI and bringing the AI to the point where it can drive the car similar as human beings do, using just vision, using just camera. Now, the cat and the fried egg example is not an anecdotal one. If we think about automated driving, whether this is ADAS or level 4 and beyond, those edge cases happen, and they happen all the time. It's not that they happen 1 in a million miles. I took here a few most advanced foundational models for the most mundane task like pedestrian detection, and I saw that every 10 minutes there was a mistake, whether it's false positive or false negative. Some of them can be understood, they're challenging. Some of them are even more difficult to understand what is the reason. And those models that are used, foundational models that were trained on billions of images, produce the same problem in edge cases. So to get a bit more technical and to showcase what is exactly the challenge here and how we solve it, You can see here basically two distributions with each of them with a long tail, a model of a cat, a model of a fried egg. And of course, we have ChatGPT or any other deep learning model on the left side. And the challenge is very clear. ChatGPT needs to learn millions of topics, millions of concepts. It has to avoid confusion between those millions of objects and millions of topics on the other side. And even if we talk about cat and the fried egg, the portion of the mistakes is extremely small. So the impact of those mistakes during the training phase on the ability of the system to learn that minimizes the average error is extremely small. Essentially, the algorithm, which focuses on the average error, becomes completely blind to those mistakes. It's completely diluted. And the result is what we call a clot. A clot is a part within a neural network that becomes blind to the ability to separate between different objects. It's blind because it was trained to do so, almost by design. The Liquid AI approach adds a very important component to the neural architecture, which we call a signature-based router. So a router is an element which identifies the clot and then takes this specific narrow population to another neural network, which can be a very small neural network. It can be an extension of the existing neural network as a branch, or it can be even a signature, a representation generated by the same neural network. But we provide a special treatment to those narrow populations. So I will take you quickly through a journey of Liquid AI. And the first process is the learning, of course. We start very similar to the classical AI approach. We take a neural network, but at a certain phase, the neural network is frozen. We don't want to get into this diminishing returns zone. So we freeze the neural network. We don't try to exhaust its performance and maximize it. Instead, we have those routers which are clustering, grouping together similar edge case scenarios and passing them to other smaller, narrow experts that are solving these specific problems. So that's the learning phase. And at a certain point, as you can see here, the architecture converges, but it's not predefined. It really maps the problem. During the inference phase, every image finds its own path within this large neural architecture. So on one hand, similar to ChatGPT and other approaches, we can create a lot of computational resources. It's much less, but still we have a lot of computational resources. But the amount of computational resources that are actually being used at every given moment is a very small fraction of the whole available resources, since every image, every specific case finds the right resources to be processed. If we do a bit zoom in into this router and signature approach, so the idea is the following. We have this frozen neural network that got exhausted. It reached maximal performance, and we don't want to get into diminishing returns. We have the router. The router key element is a signature. So the signature identifies those cat fried egg examples that cannot be separated anymore. And it doesn't try to solve them. It just goes earlier in the network. It can be as early as to the image itself, and streams those narrow streams of information to another narrow AI that now goes and does this learning phase. I will mention briefly the two concepts of Liquid AI and self-learning. So Liquid AI, as I presented, is all about splitting the big problem to smaller problems in an automated way without getting into this diminishing return zone. The self-learning capability is learning without labeled data. My talk is not focusing on that, but I will just mention that both concepts are extremely interrelated. In order to scale Liquid AI, we need this self-learning capability to avoid the limitations of labeled data. But even more important, in order to allow self-learning, which is today the holy grail of AI, to learn without billions of labeled data, just through random data, Liquid AI is necessary. Since self-learning is all about learning from sparse, weak signals that exist within the data without brute force labeling by people, the ability to generate those narrow populations is necessary. So I covered two gaps that are solved by the Liquid AI. The one is the edge cases. The second one is related to cost that is growing by addressing those edge cases. I will talk a bit about the third one, which is perception, decision, interplay, or the lack of it. If we look at the current architecture of ADAS systems, we can find two major AI systems. One is the perception. The perception is responsible for understanding the environment, describing it, and eventually producing a very short descriptive list of objects and their attributes: pedestrian, traffic signs, speeds, locations, and so on. And then the decision-making model is receiving this list and makes the right decision. And this approach, this architecture, works extremely well until level 2. So when we have predefined, well-defined scenarios, this approach is great because we can define this object list in a rigid way, in a predefined way. However, once we scale to a more open set of scenarios, like we have in autonomous driving, this approach doesn't work anymore. We need the system to be able to have this feedback loop, this interplay, to get from perception different things based on scenarios. The decision-making should guide the perception model as well. And so the trend today in the industry is to go end-to-end. If we follow Tesla recent developments, and specifically the version 12, which is supposed to be the first full self-driving version of Tesla, we see the trend to move from perception decision-making models, or in the Tesla case, 3 perception models: object detection, occupancy network, and lane detection, and a separate decision-making model responsible for planning and control, to one giant big neural network, which will then have these issues of rigid division between these two models. Or quoting Elon Musk, images in, steering, braking, and acceleration out. So it's interesting to follow the two leaders, two giants in the industry. On one side, we have Elon Musk that believes that ADAS architecture is not scalable, and we must move to the end-to-end approach. And on the other side, we have Amnon Shashua, the CEO and the brain behind Mobileye, that believes that end-to-end is neither necessary nor sufficient. The end-to-end is a one giant black box that cannot be successfully used in automotive. It's not controllable, it's not explainable, and of course, it has the same issue of the long tail of edge cases. And from Autobrains side, from our company side, we agree with both, especially in the criticism of one to another. So what would be the right approach, in our opinion? How Liquid AI, responsible for splitting a giant problem, could provide a solution? I will introduce you here briefly the architecture, which is essentially very similar to what I introduced before, but a bit more modular and focused on the end-to-end task. The idea here that we have two key blocks. One is the perception router. The perception is not responsible for generating the object list or describing the scene by bounding boxes. It is responsible for identifying the narrow scenario. So in this case, we are talking about a scenario of overtaking. And then the perception router calls one of a large set of end-to-end narrow neural networks. So we have the second model is a set, very large set. We're talking about 400,000 on small neural networks that are doing similar to Elon Musk's idea, pixels in, acceleration, steering, and brakes out. But they are doing that limited only to this narrow scenario. So the function is the following. We get the sensory input. The perception router picks the right brain, the right narrow neural network, or we call it the right skill. And the skill executes the whole task. It goes back to the pixels. It forms its own perception of the world, which is optimized for this specific skill. And then it produces the decision-making. So there is no rigid separation between decision-making and perception. But on the other hand, there is a split to smaller and more narrow problems which become affordable. To quote the city of Mobileye, it's impossible to reach the 99.9999979's accuracy with one generic perception. And we agree to that. It's really impossible. The recipe is splitting the problem and then having a dedicated learned neural network-based experts that are performing the perception and decision-making for the scenarios in one step. So we're talking about plurality of optimized perception formed within each of those agents. This is, of course, biologically plausible if we follow the observations from neuroscience. We know that different animals that have different functions also have different perceptions of the world. If you look at our agents and what is the perception, the form within their architecture, there is an example. Here you can see a perception formed by lane-centering agent. It doesn't care about objects or other elements. It cares just about the lanes, so that it becomes expert, optimal perception for the lane centering. So this approach of liquid AI and scaling the number of narrow AI agents has different benefits. One of the benefits is scalability. We can start with a very narrow functionality, ADAS functionality. We can reuse the same platform without retraining it, just by adding more and more narrow skills. We can also have a very good visibility and transparency about what the system is doing. We keep the principle of machine learning system. We don't need to engineer anything, but we still have the visibility about each and every task. And I will end with a statement basically that a lot of resources, billions of dollars and parameters and compute cycles were invested in the existing AI technology. We believe that we can disrupt this approach and solve the last 3 barriers on the way to more safe and more automated driving. We're an open company, and we, of course, are very interested in open collaboration with different players in the industry. Thank you.
Great, Igal. Thank you very much for your presentation. There are actually 2 questions coming from the audience, and I have one myself, so if you're available for these questions.
Sure.
How do you resolve conflict of interest between narrow IA agents?
Yeah, that's a very
exactly
good...
my question, sorry.
It's a very good question. So most of the time, it's about voting, right? We are using the kind of the smart of the large numbers. If more agents vote for a certain action, we believe it's the right one. More than that, we can be conservative. So if one agent is basically saying we should brake and the other agent should say we should continue to drive, we are taking the more conservative approach. Of course, there is also a policy merging those agents together, some sort of fusion. But the idea is that out of a very large ensemble of available agents, only a small number of experts is being selected. So we are not just trying to use all of them in parallel. And then the problem is fusing them.
Okay, like I just said, I had the same question. I would have phrased it a little more like an amateur, saying, when this relates to the human brain, and you have one agent saying, yes, do, and the other one, no, don't, what does your model do? But you explained it. I think I understood. Next question, how unambiguously does the router find the right skills? What happens in case of an ambiguity?
Yes, so again, it's very similar question to how we combine the agents. The same idea is about those thresholding, how we select. So for example, there can be an agent responsible for keeping distance at night, and another agent keeping distance at day. But what happens in the middle? The agents are trained with margins. So even if both of them are selected, it should cover the overlap, the area that is overlap in between of both of them.
Okay, last question. This is an interesting one. Combination of scenarios. Assume you have to brake in a roundabout. How would you deal with a combination of braking and turning?
Yes, so again, we take always the most conservative approach. There is a priority list also between the agents. If there is a need to brake, the brake will have a priority. But similar to the previous questions, the question about fusion is the right one. But here we are already fusing decisions. We are not dealing with this high-dimensional problem of understanding the environment, and selecting the right policies and so on. It's all about some kind of priority and basic mechanism which can follow, even in this case, simple guidelines.
Great, thanks a lot.
Thank you.
Thank you very much for coming here. We have a little present for you. And great talk. Enjoy your time here by us.
Thank you.
Thanks very much. Big hand.